Okay, so this is lecture number 6, 3 to 1. So we were talking about various configuration of common source amplifier. So we also understand how it's known as common source amplifier. So if this is the case, what is the gain, by the way? What is the gain? Yeah, Sudra, what is the gain for this set? What is the gain of this circuit? Okay, Manvendra, yeah. Minus G, GM. Let's call it GM1 for referring the first number transistor. Okay, into RF. Okay, this is RD by the way. RD inside with R over, right? So this is the gain we got it. Okay. Other than this, there is one important aspect. So there is one important aspect. It's known as body effect. So generally, we keep NMOS body is the fourth terminal, which we are not showing till now. But NMOS body, if it is not shown, it's connected to ground, and if it is PMOS, so PMOS body is connected to VDD. If it is not shown, if it is like this, so this indicates that the body is connected to ground in the case of NMOS, and body of PMOS is connected to VDD, right? But if it is not connected to these two terminals, it might give you something called body effect. But what body effect says, there is one equation of threshold voltage. Actually, we can call it VTH. It's also confusing in the case of Thevenin, but right now is threshold voltage. So threshold voltage is actually defined by the process or the foundry. Like you know that the threshold voltage of your BJT is something like 0.7 or something like that, right? On the basis of the fact that diode is will become forward bias when VB is more than 0.7 volts, right? So we know about this, but in the case of NMOS, it might vary. So there is one more thing, which is a function of VBS, where B stands for body and source stands for S stands for source. So this is body and this is source, and VBS is equal to VB minus VS. So if they are at different potential, body and source are at different potential, then body effect will occur. If VB is not equal to VS, then body effect will occur and your threshold voltage will change. This is changing the threshold voltage. And we also know that most of the time when body, like if you want to connect anything to 0 volt or anything you want to connect it to VDD, there are certain problems. Those problems are the ripple, right? You understand what is ripple, right? Yes or no? What is ripple? What is ripple? You told yes. So I'm asking ripple. Okay. Is there anybody who knows? Okay. Current? We are meeting after a long time, right? Okay. Manvendra or Ashish. Okay. Oscillations. Okay. What kind of oscillation? Anybody who knows the precise? Okay. Manas. Hmm? I want to apply 0 volt or I want to apply VDD. Let's talk about just VDD. I want to apply VDD, but it's not VDD, it's some oscillations. That is what you are saying. But how these oscillations are coming? Hmm? No, no. Some other thing, some other guess.
Due to the inductive effect of the probe.
Okay.
Because just like when the probe will get bounded up, will give an inductance to the.
Okay. That's also correct answer, but that's the partially correct. Maybe the effect happens because of the contribution is 0.1%. What you are saying, some 99.9% is something else. Okay. So the problem here, let's assume that I want to design. Uh, there is a circuit. Here I need 5 volt. How to generate 5 volt? How to generate 5 volt? Now you know the answer or no? Emraj. How to generate 5 volt? Hmm? That is the experiment we did it last time, right? We did some experiment last time in the laboratory. What was that? AC to DC converter, right? Rectifiers. So generally, here some rectifier, and just before that, you may have transformer, right? And before transformer, it's 220 volt AC with 50 hertz frequency for India, right? When it travels from these things and having some a big decoupling capacitor, I'm like without capacitor, I was expecting like this, and with capacitor, I'm expecting like this. But this one is not possible. Constant line is not possible because the resistance seen in this particular circuit is also contributing. So in reality, you are going to see something like this. This is known as the DC ripple. I should say not DC, AC ripple, also known as pulsating DC, right? And it's having the small signal nature. By nature, it's very small. So we can call this one as small signal. So even though our circuit, take the easier, I am considering that it's only VDD, but it's not VDD, it's something else also. VDD plus, let's say this is also common source, but with this one as PMOS, where source is connected to VDD plus some AC fluctuations or the ripples. So if source and body are not shorted together, if they are not shorted together, then this creates a body effect. Let's assume that this is connected to VDD, pure VDD, and this one has VDD plus some fluctuations, right? So both are not tied together, or both are not same. It has some difference. So in that case, how many input sources you are saying? Four. Okay. Where are those? One is VIII. Okay. Another one is Look, these two VDD are same. I made it. These two VDD are the same. So second number source, and this is third number. But as we are doing the small signal AC analysis, we are not going to consider this DC. So in that case, this becomes an amplifier which has two sources, right? So if you are applying superposition, and you understand superposition, right? In this case, we can apply superposition, right? Yes or no? Next to you. Yes, yes. Yeah. So, do you know what is superposition? You know superposition theorem. Okay, what is that? Hmm? In both what? So, when to apply superposition theorem? When to apply superposition theorem? Okay, so previous semester I am asking this, like this must be the first chapter, right? Which system is known as linear? I am not talking about time invariant, but just L in LDI system. So what is linear system? What is linear system? Which follows two theorems, hmm? Superposition and homogeneity. Right? So superposition and homogeneity only applicable to linear. However, this device is non-linear. We consider that it's piecewise linear. I mean to say, if the characteristic look like this one, VGS versus ID, then it's a non-linear. It's not linear, right? So you have to go step by step. Means there are various points. Let's say x1, x2, and so on. So in this particular region, it's linear, and I apply only analysis for small part. I am not going to apply for large signal. I am going to apply only for small signal where I can have the linear relation. So superposition is applicable with piecewise linear approximation, and in this case we can apply superposition when you are saying more than one voltage source, right? Which are small signal, by the way. Both are small signal. Look at this. This is small. This is small, right? So in that case, what to do now? Tell me. It's applicable when there are more than one voltage sources are there. I forgot your name. Sorry. Rahul. Yes, Rahul. Now tell me, Rahul. So tell me the procedure for the superposition theorem. Is there anybody who knows superposition? Karan. Okay. Saket. Yeah. So how to apply superposition theorem? What are the steps we need to follow? Okay. There is only one Saket. Okay. There are two voltage sources. Rahul, please listen to him.
So, first we will apply V and neglect the other voltage source.
Yeah. So neglect means you are going to make it zero, right? So right now, other voltage source is not there, and I am going to measure the output, right? Let's call that one as V out 1. Then the next procedure, we are going to make this one 0, and we are going to consider the next voltage source. Let's call it VDD, small signal. And then I am going to check the V out 2. I am going to take the addition of both. It will give me the final answer. right? So notably, if you are taking the V out 1, and if this is connected to V in, what is the name of this amplifier? Common source, common gate, common drain. What kind of amplifier it is? Common source, right? Source is grounded or it's an AC ground. Although VDD is connected, look at this. There is VDD is connected, which has some ripple, but right now it's AC grounded. When you are considering just V, right, and checking the V output, and the next phase of analysis, you are connecting here some voltage source named as small v with subscript dd, and this one is ground. So then what kind of amplifier it is? What is the name of this amplifier? Common source, common gate, or common drain? Hmm? Common gate, right? Because gate is AC grounded right now. Although we are doing all these things, but it's going in at the back of the mind. So when we are doing this analysis, actually it looks like this one, right? If you cannot understand, you have to follow the step-by-step things. Otherwise, you can go directly. There is no problem, right? So these two things we already knew, but we also understand that if body potential is not connected to source potential, it's going to give you body effect, and we had following small signal model, but on top of that there is fourth terminal. So this is gate, drain, source, and there is fourth terminal, body. So till now we used to connect body to source and used to make it ground. But if this is not the case, then body will also contribute some more current whose name is GMBS times VBS. I'm not going into the device equation, it's a little bit lengthy, but this current equation will be part of another course, device course. But for a understanding circuit, you just have to understand that if there is body and source are different potential, you are going to see some extra current whose value is GMB times VBS. This is the current. This is known as body effect transconductance. You can notably can see that if body and source are connected to same potential, this entire current goes to zero, right? If body and source are connected to like tied together, there is no problem. And this current is actually in shunt with this one. If you look at this, so I'm going to create a situation where you are going to see the body effect. Like this case, if I'm applying input from here, like this one is VDD, and if I connect here an input where source is not tied with the body, in that case you have to consider the body effect. Both the potentials are at different potential, so there is extra current whose value is GMBS times VBS, which is flowing in shunt with the GMVGS. So that is what we need to add, and the resistance offered by that particular branch will be 1 by GMPS, right? As we were finding out for the case of GM times VGS current. Okay. So very quickly give the answer. What is the gain of this circuit when there is effect of channel length modulation? Okay, let's start from here. If there is no channel length modulation effect, then what is the gain? Minus GM times RD. That's it. But if there is channel length modulation, then minus GM times RD in shunt with RO. But if there is body effect, then there are not only GM but GMBS is also in parallel, or you can say that somebody got the call. So the model looks like this one, right? Where this one is again source, this is gate, and this is drain. So looking from source side, what are the impedance you are going to see? 1 by GM in shunt with 1 by GMBS, because both are in parallel. Shunt. Sorry. So this is going to give me what? Is it correct? Can you check? Right? So this is the impedance looking from source side. So if there is a body effect, rest of the things are same. But the third number happens when you include the body effect. If you don't include, then the answer might be first or second. Right? So all the answers are correct, but different conditions. Are you able to follow, or is it going fast? Karan, are you able to follow? Okay, so now tell me, what is the gain when there is no channel length modulation? There is no channel length modulation. So K9 is yeah. So what is the answer? Minus GM1 divided by GM2. Okay, if there is channel length modulation, means you have to consider RO1 and RO2, then what is the answer? Am I going fast, or are you able to see? If you need to solve in your notebook, please solve that. Yeah, Suraj. Looking from here, it's same minus 1 by GM only, right? So minus GM1 1 by GM2 in shunt with RO1 in shunt with RO2 also, but you can approximate to the same answer because 1 by GM is so small value that in this case also the answer is same, right? What about the body effect? If there is body effect, so body effect means I am considering only M1 where I am giving the input. Body effect in M1, then what is going to happen? If you want to consider the body effect of M2 also, then the answer is this one. Are you able to follow or no? Rahul, are you able to follow or no? So at the back, Manas. Okay. So if this is the case, do not consider general modulation and tell me the answer for the gain. Okay, let's start from little bit lower side. What is the input impedance of this circuit? Do not consider this one. Forget about this one. Input impedance of any MOSFET circuit is infinite. Okay, so this is infinite. If you are looking into this, it's infinite. In the gate side, you are going to see only infinite. Okay, what is the output impedance of this circuit? Output impedance is measured at the output. So here, what is going to happen? What is the output impedance of this circuit? RO1 in shunt with RO2. Okay, very nice. So what is the gain? Hmm? Y0. Hmm. Okay. Uh, just to actually make clarification over here that when I am saying input impedance, this Zin is not this Zin. This is the actually I should have told source impedance. Source impedance divided by drain impedance is going to give me the gain, right? So now find out. So input impedance is still infinite. So gain is not zero. This okay. So ratio of these two are not going to give me the gain because in that case all the MOSFET circuit has input impedance as infinite. Right? We have to see from source side and drain side. Source side you are going to see GM1. What about the rest of the plant? RO1 in shunt with RO2. If channel length modulation is there, otherwise it's 1 by GM again, right? So you have to consider that. If there is body effect, then what is the gain? GMBS1 times RO1 in shunt with RO. Always check these dimensions, right? So sometimes people make mistake. So dimension wise, it's unitless quantity, right? This one is transconductance, this one is transconductance, this one is ohm. It's going to give you unitless quantity. Okay. So any problem in common source? Any problem in common source application? Raman. So just reviewing what we have done. So we have considered various loads. So this one is giving me GM1 times RD in shunt with RO1. So first expression. Second one is going to give me minus GM1 times 1 by GM2. So right? And third one is going to give me, oh sorry, I made a mistake. Right? And this one is going to give me GM1 divided by GM2, right? But what if I change this one with the source degenerative resistor? So what is the case for the first circuit? Z out remains same, right? More or less. So Z out for this one is RO1 in shunt with R2. This one is RO1 in shunt with RO2. RO1 in shunt with RO2. Hmm? Hmm? RO1 in shunt with RD. Yeah. Yeah. What about second one? Yeah, Sanskar. Yeah. So it's simple. You have to add one extra resistance looking from here. So it's 1 by GM plus RS, and you have to look at the output impedance RO1 shunt with 1 by GM2, right? So it becomes 1 by GM2 only, right? Okay, so that's the end of common source amplifier. Okay, so it's okay. Yeah. Just for the completeness, what is the advantage of source degeneration amplifier? By the source or even emitter degeneration amplifier. What is the advantage? Somebody give the correct answer. Hmm? Yeah, Gaurav. Gives better linearity. Right? If you look at the final equation, then drain current is linearly varying with gate to source potential. Right? There is no exponential term, there is no process dependency or no temperature dependency. Right? Okay, so now this source degeneration is done. Now I'm asking you to make the common gate amplifier. When you draw in your notebook, the common gate amplifier with resistive load. Common gate amplifier with resistive load. Okay, so this is hint. Okay. So, if by chance you are doing this one, as I'm seeing in most of the people's notebook, they are doing this one. this circuit won't work, right? This circuit won't work. Everything is connected to 0 volt, so it does not work. Yeah. So this one needs VDD, and this one needs some potential which will make this transistor in saturation. So let's call that one as VCM, common mode voltage. And while doing the analysis, all the common mode voltages will go to 0, right? So, so this is the circuit, let's say, known as common gate amplifier. However, I am going to keep, okay, we'll discuss this maybe in the laboratory. So this is the small signal model. This is small signal model. Vishal is not here. Eh? Vishal? No. Yeah. Now, do you remember? Do you remember small signal model? We have to replace this M1 with notably here we are connecting source to VIII and this one to ground. So body to source potentials are different. You can see. So if body and source potentials are different, then there is a body effect, and we have to consider that there is one extra current whose value is GMBS times VBS. This is because of body potential, like body effect. VB is not equal to VS, so you are going to experience body effect, right? Now this is at source, this is at gate, and this is at drain. If we map this is gate, this is drain, and this one is source, right? So source is connected with potential called V in, right? So where should I connect gate, Vishal? In this small signal, what should I connect to gate? By the way, this VB is bias potential. Some people write it common mode, all are same, right? Or some people write it VDC also. So what should I do? Sorry? Ground. Okay. So it has to be grounded because this is AC ground, right? What about drain? At drain it's V out, but there is one resistance whose value is RT, should go to ground because this part is connected to VDD. This is actually VDD, but as we are doing AC analysis, so it becomes AC ground. So any doubt in understanding this small signal model? Somebody? If there is anybody who has problem? If no problem, then this is the answer, right? So I replace that GMBS, GMB times VBS. Some books are writing GMB, some books are writing GMBS. Both are same. Both are body effect transconductor. So I replace that with a resistance whose value is 1 by GMB. Oh, sorry, 1 by GMB, and one current is already flowing from here. So now you have to tell me the current. You have to tell me two impedances. One is in source side, one is at output side. Output side it's easy, right? Can you find out the output impedance? Output impedance will be measured at the output. R0 1 in shunt with RD, right? So this side is R1, this side RD. Input impedance still is in this case, if you are looking at the source side, what is the impedance you are going to see? Hmm? What you are saying? 1 by GM. You might be correct. You can tell me. 1 by GM. Okay. Your answer is 1 by GM. Somebody else who wants to give other answer than 1 by GM. In this case, there will be body effect. 1 by GM plus in shunt with 1 by GMB. Right? Right? You have to note that when you are finding out the source impedance, you are giving the known Thevenin potential from this side, right? Earlier we used to do that, and when we were doing this, we were experiencing that the current is flowing in this direction, which was opposite. But in the case of common gate amplifier, VGS is actually 0 minus Vin. Can you see? Where gate potential is 0 and source potential is Vin. So current is actually not this direction, but the current direction is going in reverse direction because of VGS. In other case, input was applied here where VGS was actually positive. But in this case, it's negative, and that's why the gain looking into common gate is not become negative, but it becomes positive only. So here, if I look at the gain, it's not negative, it's positive. Whereas looking into common source, the gain is actually negative. From here to here, it's negative, but from here to here, it's positive, and the gain is actually equal to GM plus GMBS times RO1 in shunt with RD. In common gate amplifier, you will always have body effect, and you have to consider that one. You cannot drop that, right? So the answer will look like this. If there is a relation between GM and GMB, if GMBS is eta times GM, then I can write down that the gain is equal to 1 plus eta times GM times RO1 in shunt with RD, right? So this is the gain, but with the positive sign. It's not negative, it's positive sign. Okay, so if you follow that, so you can make three remarks. The small signal gain of the amplifier is positive. Similar gain of the common source amplifier. In that, GMB was not included. Here, GMB is included. And because of positive, it's always in phase output. In phase output means both are in same phase, right? And in the case of common source, it's 180-degree phase shifted because the gain is minus, right? So if this is connected to VB or maybe VCM, and if this is VDD, tell me the gain. What is the gain of this circuit? RO1 in shunt with RO2 divided by
1 by GM1
yeah, so 1 by GM1 in shunt with 1 by GMB2 B1, right? And that is going to give me GM1 plus GMB1 into RO1 in shunt with RO2, right? If I change this one, to this one. Now tell me what is the gain. Right? This is an approximated. Right? Okay. If I do this one, so this is PMOS. Now what is the gain? Yeah, Sakit. Rupanji. Okay. 1 by GM, then GM1 plus GM2. This is what you are saying? Okay. Can you be a little bit louder? GM1 plus GMT1. Very nice. 1, okay. Let's call this one as M3. 1 by GM2, okay. RO3. Still you can approximate this to same value because RO3 is much higher than 1 by GM2, right? Okay. However, if this is the case, 1 by CM VCM3, okay, then what will be the answer? Yeah, yeah, RO1. Right? So it's very easy, right? Now, so now notably we have to understand if there are two configurations we have studied. If I am asking you to find out input and output impedance of this circuit, what is the input impedance of this circuit? Infinity. And output impedance of this circuit? RO in shunt with RD. Generally, this is also very large number, right? As large as we can call it infinity. So input impedance is infinity, output impedance is infinity in the case of common source amplifier. So what kind of amplifier this one is? Yes. Whereas same MOSFET when connected in common gate amplifier, can you tell me what is the input impedance and what is the output impedance? What is the input impedance? 1 by GM, and this one is same as previous one, RO with RT, so you can approximate it to infinity. 1 by GM is so small, you can call it as low as 0. What kind of amplifier this one is? So it depends what configuration you are connecting. Now let's talk about this one. Look at the arrows, where the arrows are connected, right? So now tell me, what is the input impedance in this circuit? Infinity, very nice. What is the output impedance? 1 by GM in shunt with RT. So this is as low as 1 by GM, or you can call it 0. So this one, voltage control, voltage source. This is also known as voltage follower. So we'll study in next class voltage follower. This is also known as buffer, and this is also known as driver circuit. because the gain of this circuit is approximately 1. But this is actually voltage controlled voltage source, or we can say that it will give you, it will not give you loading effect. But in the case of common gate, as the input is 0, if you are going to apply directly anything over here, it will load because the input impedance is 1 by 3. Whereas in this case, it's separate. So in general, like to categorize this uh, this MOSFET as voltage controlled current source or current controlled voltage source or whatever, but it depends on which configuration you are choosing. That is more important, right? So it depends on the configuration rather than calling it separately, right? So it can be like the MOSFET can be categorized as voltage controlled current source or maybe triple CS or VCBS. Depends on your configuration. Okay, so we'll talk about common drain next time.